Would you take your packet and, assuming that you haven't lost it, go to number 10?
10. Okay.
I didn't use any names, did I?
Mr. Moore, should I put the thing?
Yes. Are we on now?
Yep.
Oh.
Hi.
And there was number 10.
Actually, no one cares about it.
Wow, Rob, really? I don't care about you either.
I speak the truth.
The YouTube page.
We are no longer friends.
And the link to it is on our headline homepage. All right, so hello, Anna and Mohammed. Looks like Mohammed's not here. And Amruth, of course. And others. Yes?
Just kidding.
What is it with this class?
I never. What? People don't have
I'm so smart. I'm so
Or you think 7-Eleven is a ghetto store?
Look at number 10. Yes? Oh, I forgot to do that. I told you I would, then I didn't.
Nice, Mr. Moore.
more.
I'll put them on there. Okay, like, I know that I have a couple of days. Did anybody try to start the problems yet?
God.
I have
Maple?
I procrastinate until like the last.
You thought about it.
I was, Mr. Moore, I was
All right,
thinking about
anyway,
thinking
no,
about
we
doing
can't
it,
be
so-
chit-chatting all hour. Number 10, take a look at that one. It's the relationship between KC and KP. Try that one. Can we get that one on our recording? Okay. Now, you should do this one without a calculator.
You're so nice.
Yes. You know how when we use the ideal gas law,
Wait, how are we supposed to do
you
that?
know how we had 3 different values of R depending on the pressure unit? The R, when it was in atmospheres, was 0.0821.
We don't know how to do that.
Yes, you do. That one you do.
No, wait,
That's
no.
973 times.
That's where we get that
10821 to the power of.
T must be in Kelvin. T is always in Kelvin except when you have delta T. Then you can leave it in Celsius and take the difference. But yeah, anytime you have just a straight T, that means use Kelvin.
Oh.
What?
I got it.
The 273? This equation? Yeah.
So it's 700.
Yes?
It's A, right?
What's 700 plus 9? 73.
Before you get too much into this problem,
Wait a minute.
in fact, that's what I'm listening for. Just keep trying the
You
problem.
lie. Oh, it is.
That's what I want, yes.
Oh my god! I just got
What?
it.
If you don't see it, then keep doing it.
If you don't see it, you're blind.
Thank you.
Or H.
Oh.
Oh, it's that. Oh, that's. I love that sound. Keep doing it.
Wait, so is it A?
What did you find?
This is a trick.
Yes. All right. I've heard that enough times now. Can I have your attention again? I'll tell you, Project. Whatever KC is, and we know KC in this problem, don't we? KC times RT to the power, whatever the delta N of gas, the change of moles of gas. In this equation, this doesn't always happen, but in this one, we had 2 moles of gas on the left and 2 moles of gas on the right. So the delta N of gas is 0. So this whole term is raised to the 0 power, which means that Kp equals Kc. That's the only time that these two things are equal to each other, is when you have the same number of moles of gas on both sides.
Nice.
Wow.
Yeah.
That's why I said don't use a calculator.
That was nice.
After this, you can use one.
Tricky.
Only gases, yes. So like if you have a solid and a gas on the left, you don't count the solid at all.
But then you know,
I know.
oh, I already know this.
Say, you know how you give us special credit if we make a mistake in your Say we subtract weird and don't get 0 for this problem, we get like 1. Would you still give us special credit?
Yes, you would.
Yeah, I'd give you probably 1 out of 10. Minus 9 for that one.
He's not kidding.
You mean minus 1.
Which question?
Oh, see what I did? Good. I'm good.
Try number 11. Same idea, but try number 11.
It's a trick question.
With a calculator.
And here's number
Well,
1.
you'll have to try it. See.
So this is a trick.
That 5-minute thing there.
How come you're not panning around?
I love
the
to hear that
classroom?
chorus of, oh. That's, that's not
Hey,
it.
Mr. Moore.
If
Mr.
you need to
Moore,
leave the room, go ahead.
can you hold this up for me? I need to focus.
What's that?
Can you hold this up in front of the camera for me? I need to focus. So.
3 minus 12.
Sounds like a lot of people need to focus in here.
Oh, burn.
Yep, got it.
So much burn that it took out
This
the
is
air
4th
nomad.
hour again if you didn't figure it out.
So much burn that it took out the
So-
air nomad.
Oh.
My group of rowdies in here.
I get it.
What's
Anna,
3
you know.
minus 5? What's 3 minus 5?
I believe it's negative pi.
Oh, that's a great answer.
Pot of beans, pot of-
No, use a calculator. I just meant that last one. I didn't want to.
Wait, so for R, do we use like 0.08? We use 0.00 if we want a 0.0.
1 0. It's this thing up here.
Wow.
So that's 3.
Guys, help me.
God, really neat.
Yeah, see, big rock.
All right, gang. Can you get an answer for that? It's not very hard. We don't need to take all day to do this. You get C for your answer?
See, senor.
I'm not getting it.
Ah, very good.
I'm not getting it.
Yes, you are.
Darn it.
Take the KC and multiply it by 0.0821 times the temperature. That
Oh, yeah.
climate raised to the negative 2
Is it
power.
C? Why do people get so
Okay, we're moving on.
No, because it's
All right, gang. Gentlemen in the back, can I have your attention, please? Nabil? Anit?
I got it.
Okay, listen. The number 13 is going to introduce a new concept to us. Would you take a look at number 13? And we're going to have to use what's called an ice table for this one, but look at the problem first. We have decomposition of PCl5.
Thanks.
It says PCl5 is put into a reaction vessel to give an initial pressure of 2.74 at that temperature. Calculate the pressure of PCl5 after the system has reached equilibrium. 13. So let's see. We have a reaction at equilibrium, and the question is, after the reaction is, well, that reaction is begun, and then at equilibrium, what is the new pressure of it? Anytime that a problem involves an initial and a final amount of something when it's involving equilibrium, you're going to use an ice table. Ice tables, it's not anything to do with frozen water ice. It's an acronym. And it stands for initial, change, and equilibrium. Even if you are one that takes shortcuts when you do problem solving, you will probably want to use ice tables throughout our whole study of equilibrium reactions. That means that you're going to be doing ice tables all the time. You're probably going to do more than 100 ice tables before it's all over.
Wow.
That's a lot. It's a great way to organize your thinking and your work. Now, as you get used to equilibrium problems over time, you will start to recognize, oh, I don't need to use an ice table every time. You'll do a lot of these. Initial means how much was there before any reaction occurred. And the problem tells us something about what happened initially. It was 2.74 atmospheres of the reactant were added to a vessel. There was no PCl3 or Cl2, so the products were 0. Normally the products are 0, at the beginning at least. The K is given to us as 1.8. What does a K of 1.8 mean? What does that mean about the reaction?
There's 1.8 times for products, or the pressure of the products is 1.8 times more than the reactants.
Right. There's going to be more products than reactants at equilibrium, right? Is this reaction right now at equilibrium?
No.
No, because the this value, 0 divided by that, is not equal to that, right? There's another term that we talked about back in the thermo chapter. That term was Q, the reaction quotient. That's also products over reactants, but that's at any point in the reaction. So at the beginning of reaction, Q equals 0 because it's products over reactants. And Q changes as the reaction proceeds. Q gets bigger because the products go up as the reactants go down. So Q grows and grows and grows until Q equals K, then the reaction stops because it's in equilibrium. And if you have a case where Q is greater than K, it's going to shift back to the left to drop Q down to equal to K. Q is just an indication of where the reaction is. So this reaction has a Q equal to 0. Anytime Q is less than K, it's going to shift to the right until Q equals K. Now, I don't have any more of this filled out, but we can do it. The change. How much does PCl5 change? If we know that the reaction is going to the right, what's going to happen to the pressure of PCl5?
Go down.
It's going to go down. Do we know how much it goes down? Well, 1.8 represents the equilibrium ratio of that to that, products to reactants. We know that this is going to go down, but I don't know yet how much it's going to go down, so I'm just going to say it goes down by some amount x. And if this goes down by x, what's going to happen to the pressure of PCl3? Also by x, because it's a 1-to-1 ratio. Every time 1 mole of this goes down, 1 mole of that goes up. Right? Beneath?
Wait, for pressure, don't you have to use like the PV energy thing?
No,
Oh.
because we're already in pressures.
Oh. Oh.
If we had like moles or whatever we need pressure, then we'd have to use that. But we're already dealing with pressure, so we just see how the pressure changes. And the ratio of pressures is the same as the ratio of moles as long as the other terms are constant. Okay? So the Cl2, same thing, is going to go up by x. You okay with that? So at equilibrium, this is going to be whatever it started as 2.74 minus that amount x. At equilibrium, this PCl3, which started with none of it, it went up by some amount x. So at equilibrium, the pressure of it is x, and the same thing for the Cl2. Okay, now what is the question? What's it trying to ask us to try to find? Calculate the pressure of PCl5. This term right here is what we want, so we're going to have to find x. Yes? Now, I apologize for what's about to happen.
If there is calculus,
This is so much fun.
No calculus.
That wouldn't be fair for us. Oh my god. Is it physics?
It's worse.
Oh my god. Is it addition?
logarithms, then no.
Kp is 1.8, right? That's what it was up there, 1.80. And that's equal to the product concentration over the reactant concentration.
Oh,
Well, yes. The product concentration is x times x, which is, I say concentration, pressures of it. X times x over that term,
Oh, quadratic.
solve for x.
Oh no.
Oh, that's.
You gotta use the quadratic formula.
Oh, no.
Hey, can we dive into the graphic calculator?
It's okay because I apologize.
Use a graphic
No, wait, there's a
calculator.
way around it. Why would you apologize? I like it.
There's no way around. You gotta use the quadratic formula.
Use a graphic.
Yes, sir?
Our calculator's allowed.
Yes? You may be sharp with your calculator and either know that there is a quadratic solver on your calculator and or you could graph it and find the 0 points. Now, do you know that a quadratic formula will give you 2 different answers?
No.
When you do the quadratic formula with these problems, one of the 2 answers is always going to be bogus. For one of the 2 answers you get, you can be able to throw it out. The other one you're going to keep, and that'll be your answer.
It can't be more than 2.7.
Right, and yeah, you can't have both answers. One of them is going to be wrong. For instance, is it possible to have a negative pressure? So if you get an x that